Previously, we had SN2 reactions, which is when sodium hydroxide acted like a strong nucleophile and attacked this carbon from the backside to replace this leaving group. Now, what if sodium hydroxide acts like a strong base? We get something called an elimination reaction. So, the way this works is that when you have a strong base, it has a lone pair that's available to attack, and it will attack the alpha hydrogens. So, the alpha hydrogens in this situation are these hydrogens right here. Now, what's special about them is that they are right next to the leaving group. Over here we have our leaving group, which is the bromine, and the carbons on next to it are the alpha carbons. So those are alpha hydrogens. Now, our oxygen, which is our strong base, will either attack this hydrogen or this hydrogen right here on the carbon right next to bromine, and we can get up to two products. We can get a product that has a double bond on this carbon. So you'd have a double bond carbon like this with two hydrogens over here. And then you get a single bond carbon here, single bond carbon, and you have your two hydrogens, and you have your three hydrogens. So that's your first possible product. And your second possible product is a single bond carbon here and a double bond down this second and third carbon. You have a single hydrogen over here, single hydrogen over here, and three hydrogens over here, and three over here. Now these are your two possible products for doing an elimination reaction, where essentially this strong base attacks this hydrogen, and the bond right over here will essentially go to the carbon, essentially. Rather, not even go to the carbon, but go form a double bond with the carbon with the leaving group, and the leaving group will take a lone pair with it and leave, and you get that double bond right there. And if it attacked this hydrogen over here, these two electrons basically form a pi bond with this carbon, and then the halogen leaves again, and you form this pi bond. And so that's an elimination reaction. You get a double bond. That's the basics of it. And so if you have sodium hydroxide, you get up to two products. Now, the product down the middle over here and the product with a pi bond on the outside, these are two different products that can be manipulated. We can actually have something prefer this product or that product depending on the base that we use. Now, generally, by alkene stability, the more substituted an alkene is, the more stable it is. So over here, since we have a 2 carbon bonds to our alkene, it's di-substituted. And over here, we have 1 carbon bond to it, so it's only mono-substituted. So this is actually more stable because it's more substituted. And this is called the Zaitsev product. So the Zaitsev product is the one that is more substituted, and for our here, which is less stable, it's our Hofmann product. And so these two can be manipulated. You can use a different type of base to get either of these, and we will show that in the next few examples. But first, let's talk about how we can manipulate a strong base and a strong nucleophile like sodium hydroxide to prefer an elimination reaction.